So we're starting out today with doing a in-class exercise where I'm actually going to have you guys get into groups. So I have 3 different pictures, and this is one of them. And on that, each picture, there's 4 different things, A, B, C, and D. And you're supposed to decide which picture does not belong, and then think about it. Why doesn't it belong? And then you're going to come back in like 2 or 3 minutes after you look at this. And then you're going to tell me which one you don't think belongs. I'll ask you guys all at the same time. And then I'll get you guys into groups. So those who all chose A, I'll put you into a group. Those who chose B, I'll get you into a group, etc. Unless you all choose the same thing. And then you guys will discuss in groups why you chose the letter you chose, see if you guys all agree. And then you're going to come back into the class and then explain why your group chose what it did. And so there's actually no right or wrong answer. So just to let you know that. So I'm going to pause the video and then I'm going to give you guys, like 3 minutes to kind of look at it. You might have had some time to look at it already, and then I'll get you into groups once you tell me what you like. So we had a chance, looked at the picture. Students discussed it, went into breakout rooms, depending on what they had chosen, and came back and explained. Got some really good reasoning behind why people chose the one they did. And so now looking at the next one, you want to decide which one doesn't belong, A, B, C, or D, and come up with reasoning why you think that's the reason why it doesn't belong. Okay, so again, great discussion on the last picture, good reasoning on why one didn't belong versus the others. So now this is the last one we're looking at. So out of these 4, which one doesn't belong and why? And then give reasoning behind it. Let me just pause this for now. Okay, so we just got done with the exercise and I just looked at this number C and wanted to talk about that limit and go through showing what the limit as x goes to negative infinity of that function is. And so let's look at this. So we have the limit. And I'm going to zoom it in. No. As x is going to negative infinity of 2 all over x plus 2. Oops, 2 to the x. All over x plus 1. That's what I meant to say. So notice when we plug in negative infinity here for x, so this would give me 2 raised to the negative infinity all over negative infinity plus 1. Let's use rules of exponents to manipulate this. So rules of exponents is power to power is multiplication. So I'm going to go backwards. Instead, I'm going to take the multiplication and rewrite it. So I can think of this as 2 to the infinity times negative 1 all over negative infinity plus 1. Why did I want to? Okay, let's look at it this way then. I'm going to put brackets around this. So now I want to look at another fact of exponents. And these are going to be really helpful. Rules of exponents are really helpful in this class. Remember that if you have a negative exponent and it's in the numerator, we can bring it down into the denominator and make that exponent positive. And so let's do that. So this is going to equal. So I'm going to bring this down here. So this is 1 over 2 raised to the infinity all over negative infinity plus 1. But if we have 1 over something that is getting huge, that piece goes to 0. And so we can say that 0 over some number is also going to go to 0. So 0 over negative infinity is equal to 0. Okay, so there's one type, and I just thought that that looked like a good thing just to talk about. And then let's look at another one. Let me let you guys write that down. Another one that's going to be useful, and it will be helpful to use this fact, is the following. So if we have the limit as x is going to, and this is the case for either positive or negative infinity, plus or minus infinity. And just for time's sake, I'm putting them both in there, of sine x over x. If we use the sandwich theorem, we can show that this actually is equal to 0. And so let's look at this. Using the sandwich theorem, remember the graph of sine of x? If you look at the graph of sine of x, y equals sine of x, that range is always between a negative 1 and 1. So if I looked at this graph of sine of x, it comes down like this. Actually, that's cosine, but same sort of reasoning with cosine. Looks like this. And all the y values are always between, unless we have some number out here, between negative 1 and 1. And so if we think about the absolute value of this, so absolute value of sine of x over x, well, if I take the absolute value of this number is always going to be between 0 and 1 because the negative 1. So it's always going to be bigger than 0. And this will actually always be bigger than or equal to 1 over x, the absolute value. And so knowing that, and if we took the limit as x goes to positive or negative infinity, things are jumping around. Limit as x is going to positive or negative infinity of 0, this has to be less than or equal to the limit as x is going to the absolute value. Let's do it here. Sine x over x plus or minus infinity, which is less than or equal to the limit as x is going to plus or minus infinity of 1 over x, absolute value. Well, limit of a constant is always the constant. So this piece right here, this is equal to 0. This is less than or equal to the limit as x goes to plus or minus infinity of this. So this is less than or equal to, well, when we take 1 over going to infinity or negative infinity and taking the absolute value, doesn't matter though, this also goes to 0. And so we can say that this limit here then has to go to 0. So therefore, the limit as x goes to plus or minus positive infinity of sine x over x is equal to 0. If you go and you graph it, what happens is it starts oscillating back and forth, but then it starts hugging this line. In here. And remember, the other one that was really important for us is if we're looking at the limit as x is approaching 0 of this value, we saw that it doesn't exist when x is 0, but that was approaching 1. And we used that bit to help us sometimes solve limits. I'm going to do one more example. I know it's past just turn time for class to end, but you're welcome to stay if you want to see one more example. You probably have one like this on the homework, where you have a limit as x is approaching infinity of the following: the square root of x squared plus 25 minus the square root of x squared minus 1. If you have something where you get infinity minus infinity, or negative infinity minus infinity, that just doesn't make sense, or negative infinity plus infinity. Those things don't make sense. And so that's like an indeterminate form. And so we have to manipulate this. And the way to manipulate this one when you have radicals is to multiply by that fancy one. And that fancy one is going to be the conjugate of what this radical is. And so we'll look at the limit then. As x is approaching infinity of this piece, square root of x squared plus 25 minus the square root of x squared minus 1. We're going to multiply this all by the square root of, and that should be all, the square root of x plus 25 plus the square root of x squared minus 1. Unfortunately, because of the addition in between, we can't just break this down. And these all both have x squares. So a lot of students would like to say x squared plus 25, the square root of that whole thing is x plus 5, and that is totally wrong. So don't do it. It's really tempting to. And then whatever we do to the numerator, we have to do to the denominator. So we're multiplying the bottom by x squared plus 25 plus the square root of x squared minus 1. Okay, so when we're multiplying by the conjugate of the radicals, think of this as a minus b times a plus b, which is a difference of square, a squared minus b squared. And so let's just look at that, doing it that way instead of FOILing out and then canceling out middle terms. So this is the same thing as x squared plus 25, that value quantity squared, minus this x squared minus 1, that quantity squared, all over, and I'm not going to manipulate this. I'm just going to leave it as square root of x squared plus 25 plus the square root of x squared minus 1. So squaring a square root, that's nice because that gets rid of the radical. And so we have the square root of x squared plus 25 squared gives us what's underneath, which is called a radicand, x squared plus 25 minus, you got to be careful because there's more than one quantity here, put parentheses. So squaring this radical, we have x squared minus 1 all over the denominator, square root of x squared plus 25 plus the square root of x squared minus 1. Let's distribute that negative and combine like terms. Limit as x is going to infinity of x squared. This is now going to be minus x squared from distributing that negative. I have a plus 25 here and a plus 1, so that's really plus 26. So notice my my numerator, those x squared cancels, and just for time's sake, I'm going to just erase those. And we're just left with 26 in the numerator. And so now when we plug in infinity, wherever we see an x, we have infinity in the denominator and a number in a constant in our numerator. So 26 over something that's getting huge, going to infinity, this value would have to be going to 0. There, I just wanted to add a couple of examples I wanted to show you to finish up that last section in chapter 2. And so thank you for bearing with me and staying a couple minutes after class. So let me stop the video.